In the previous two videos, I looked at the conditions that we need to make valid inferences in multiple regression and showed you some ways in which we can detect violations of those conditions using our data. Now, let me talk a little bit here about why it's important that we meet these conditions. So the first one is independence of observations. Why is that important? Well, if you'll remember from when you studied your initial statistics and you talked a little bit about probability, that one of the things you learned about probability, I know in my courses I don't go into a lot of detail about it, but I do mention it, and that's the idea of joint probability. That is the probabilities associated with multiple events. And when those events are independent of one another, you can take those probabilities, and I'm gonna use real rough shorthand notation here. This is normally this is not the way we would do it. We would normally have like a x equals x1 and so forth. But I'm just going to use real rough notation and say, let's just call the probability of event and the probability of another event and the probability of another event. And what is an event? Well, in our particular example that we've been working on here, an event is the actual observation of data. So we have 53 of them. And we're looking at those 53 events, and we're asking ourselves the question right now, why is it important that those events all be independent? Because if you want to calculate the probability of all those events happening at once, they have to be independent for you to be able to multiply them together. And that's how we actually calculate our probabilities when we're doing our inferences. Remember that inference, one of the components of inference is a probability distribution. And so we're calculating based upon multiplying together these various probabilities. So if you do not have independence, then that joint probability rule breaks down. So that's the reason we need that. Let's see, what was the next one we had here? It was that the data can be fit with a linear model. Well, that should make sense to you. If we come back here and look at a model, how do we interpret our regression coefficient? I'm just going to go ahead and think about simple linear regression here. And we have the points, and we have a line going through the points. And when we say things like, oh, the slope of that line is 5, how do we interpret that? What we say is that tells us that for every unit change in x, that for each unit change in x, we're going up 5 units in y. Well, wait a minute now. If you had something like this, where it was curvilinear, would it make sense to say that for every unit change in x, you go up 5 in y? Because down here, the change is not nearly as much as it is when we look up here. So if it's curvilinear, those statements about those coefficients don't make a lot of sense. You're trying to talk about something along the range of x that in fact changes along the range of x if you have curvilinear data. So that is why it's important that we have a linear model. What about the variability of errors being homoscedastic? Why is that important? Well, let's think again about if we had heteroscedastic, what that would mean. Well, if you have heteroscedastic data, something like, let's say this, okay, what you're doing with those data is you're trying to estimate the standard error of a coefficient. You're estimating a standard error of a coefficient, a standard error. I'm going to put the emphasis. You're estimating a standard error of the coefficient. That is one number. And you're saying that that coefficient has an error, one particular value. But if you look here, if I had a regression line here, I have a different variation here, different variation here, different variation in all those spots. And estimating that with one number is not going to cut it. But think about when you calculate your confidence interval for the coefficient, what do? You take some probability distribution value and multiply it by the standard error, a single number. And so you're trying to use a single number, whereas if it was homoscedastic, a single number makes sense because you have the same variation all along, and so you can estimate what that variation is. You use a single number there when you have heteroscedastic values, and you're not going to get accurate confidence intervals or accurate p-values or any accurate inference from this. We've already talked about the conditional distribution of E being normal. Why is that important? Because of the probability distribution. Again, that margin of error has a probability distribution associated with it and a standard error associated with it. So whereas the homoscedasticity talks about the standard error part, the conditional distribution of residuals talks about the probability distribution part. And you need to have your variation, your residuals be normally distributed, not variation, that's the homoscedastic. Your residuals be normally distributed, and if they are, then you know what probability distribution to use in order to calculate your margin of errors. You know that if you estimate the variance, you can actually use a t-distribution, but the t-distribution relies on the normal distribution. The thing that's different is that instead of knowing the variance, we're estimating it. So you have to have a normal distribution. Now, as we've said, if you have a large enough data set, this is okay. You can get by without this condition. But you know what? A large data set doesn't do anything with homoscedastic, and it doesn't do anything with this linear model here. So it only addresses one of the conditions. So a large data set does not fix all the problems. And then we've talked about the explanatory variables being measured without error. Why is that important that they're measured without error? Well, if you go back to our simple linear regression here, so what I'm doing is I'm talking about for a value of x that's right here, when in fact, if that value of x really is somewhere along there and you're saying it's right here, then you're going to be off in your statements about the relationship of x and y, because if a value of x represents a whole bunch of values in here because of the unreliability of your instrument, you can see how that's going to change what you can actually say. So, and we talked about the fact you never actually have that, but at least you want good reliability in order to be able to make reasonable claims with your multiple regression analysis. So those are the reasons that we have all those. Again, this has nothing to do with the validity of your coefficient estimates for your particular data, because every time we do statistics, there's two parts, and I always remind my students of that. There is the part about what actually happened in your study, and your multiple regression can answer that question even if you don't have these conditions met. It can answer the question about what actually happened in our study. But when we start to then infer outside of the study and what's going to happen if we take another sample, now we're getting into the realm of inference. But don't forget the importance of description, the importance of graphical displays, the importance of saying, here's what happened with the participants that I observed. In the case that we're doing, here's what happened in the small cities that I observed. Now, can I make some statements about all of the small cities? That's the inference part. Okay? All right. I will see you as we move along to the next topic in the next video.